Hello everyone, welcome to the video lectures on fluid mechanics. In this video, we are going to start a new module, that is a laminar and turbulent flow. Now, what is a laminar flow and what is a turbulent flow, or when we call the flow is laminar and when we call the flow is turbulent? The highly ordered fluid motion characterized by smooth layer of fluids is called as a laminar flow. In other words, we can say the laminar flow is a type of flow in which there is no significant mixing of neighboring fluid particles. Right? Then we call that flow as a laminar flow. Right? Now, when we call the flow is turbulent, that means when the fluid particle vary irregularly so that the quantities such as velocity, pressure shows the random variation in time and space coordinate, or else we can say the highly disordered fluid motion that typically occurs with high velocity is characterized by velocity fluctuation, then we call the fluid is turbulent flow. Right. This laminar and turbulent flow is coined by a famous scientist called a Reynolds, that is demonstrated in 1883 here. Right. Now, what is a Reynolds number? Reynolds number is defined as a ratio of inertia force of fluid to the viscous force. That is a ratio of inertia force to the viscous force here. Right. That means we will be considering the fluid flow which possesses the velocity v, the diameter of pipe is d, and the density of the fluid is rho, right, and kinematic viscosity is mu. In case if it is a pipe flow, if it is non-pipe flow or open channel, we will be considering the velocity of fluid is v and length of the flow or length of the flow is L and density rho and mu is the kinematic viscosity. We will be considering dynamic viscosity of a fluid here. Right. These things we will be considering. Right. Now, Reynolds number is what? Inertia force by viscous force, that is rho VL by mu or rho VD by mu. How we got this one here is Reynolds number, it is a ratio of inertia force of flowing fluid to the viscous force here. Right. Now, inertia force, inertia means it is mass into acceleration of a fluid here. Now, what is density? Density is written in terms of kg per meter cube, that is mass by volume of a fluid here. Only we need is mass, right? Mass is what? It is density into volume, here. Now, inertia force is density into volume, it is mass, into acceleration of a fluid is velocity by time. Right. Now, volume by velocity is nothing but a discharge, that is meter cube per second is discharge here, that is volume by time is discharge q. Q I can write in terms of area into velocity here. So, in place of volume by time, I will be substituting in terms of area into velocity here. That means Fi is the inertia force rho a v into v. So, Fi becomes rho a v square. Now, next one is the viscous force. Viscous force here is nothing but the shear stress into area. Viscous force is shear stress into area here. Shear stress is mu into du by dy. Mu into du by dy is the shear stress here, right, into area A. Right. Now, shear stress mu into du by dy, du is what? Du is the change in velocity, or I can take it as velocity v. Dy is the linear distance, that is L. So, I can write mu into v by L into A is the viscous force. We got the viscous force, we got the inertia force. So, now I will be substituting it in the Reynolds number formula here, that is inertia force by viscous force, that is rho a v square is the inertia force, and viscous force is mu into v by L into A, mu into v by L into A. So this velocity square and velocity will get cancels off, remaining will be only velocity, area will get cancels off, and then I can write this as rho v L by mu. This is the Reynolds number, it is a linear distance. When we have a pipe flow, this L is replaced by diameter of pipe. So I will be getting rho v d by mu, right? Or it is a kinematic viscosity is what? Kinematic viscosity is dynamic viscosity by density. So I can write here, this is the dynamic viscosity, density if I take it down, VL by nu. Kinematic viscosity, dynamic viscosity by density is kinematic viscosity nu. Similarly, for a diameter of a pipe, Vd by nu, it is the kinematic viscosity here. That is, nu is the kinematic viscosity. So in brief, I can state Reynolds number is rho v L by mu or rho v d by mu here, right? Now, when the Reynolds number is less than 2000, when the Reynolds number is less than 2000, then we call the flow is laminar. When the Reynolds number is more than 2000, we take it as turbulent. Right. This is how we differentiate the flow is laminar and the flow is turbulent. This is with respect to the pipe flow here. Now, I told the Reynolds is the scientist who coined this term, that is laminar and turbulent. Now, how he got this one is with respect to the Reynolds experiment. Right. In Reynolds experiment, what he has done here is he has taken a tank filled with a fluid. Let us say it is water. He has taken a tank which is filled with a fluid, that is water, and one more small pot where it is been filled with a dye ink. There it is filled with a dye ink here. Right. Now, what he has done, this dye ink, and he has taken a long pipe, long glass pipe here. He has taken a long glass pipe here and it is open to the atmosphere. Right. Now, after this, what he has done, a small diameter pipe he has taken and dye ink is left in the center of the pipe. Dye ink is left in the center of the pipe here. Now, when the flow is moving, when the water is flowing in this pipe, if the flow velocity is very less, so there will be a laminates which is moving. That means the flow will be laminar. So there will be no further mixing of the fluid particles here. That means one layer over another layer. The fluid will be moving with one layer over another layer. So there will be a continuous dye ink which is moving only in the center of the pipe. So he told then the flow is laminar. Now after this, he started increasing the velocity of fluid. He started increasing the velocity of fluid. When the fluid velocity is increased, this dye ink started mixing with the other fluid. Right? Dye ink started mixing with the other fluid. That means the molecules are shifting from one layer to another layer, or the molecules are not moving in laminates here. Molecules are not moving in laminates here. If just it started, then that flow is called as a transition flow. That means conversion from laminar flow to turbulent flow. If the mixing is more, then he told the flow is turbulent. Right? Then he told the flow is turbulent. Right? Most of the case we take turbulent flow as 3000, more than 3000, that is Reynolds number is, when the Reynolds number is more than 3000, then he told the flow is turbulent. That is from 2000 to 3000, he told the flow is a transition here. That means converting from the laminar to turbulent here. Right? That means here in turbulent flow what happens, the molecules will start moving from one layer to another layer, or the molecules will start crossing each other. So we can easily recognize the dye ink which is moving or which is crossing the layers here. Then he told that flow is turbulent flow. This is what the Reynolds experiment is. Right. Next, going to the next part of this one, that is entrance region and fully developed region for a laminar flow. How does the laminar flow happens in this? Right. Now what we have done, we have considered a fluid entering in a circular pipe with uniform velocity here. Right. With uniform velocity, the fluid is entering here. Due to no slip condition, the fluid particles which is in contact with the pipe wall here will gradually pipe wall here will come to stop. That means when we have a fluid which is flowing on the surface, on this point, which is the fluid which is in contact with the surface of the plate, here the velocity will be 0. Velocity will be 0, and the velocity when it is there at little bit higher point, the velocity will increase. Right? When little bit higher, the velocity will be more than the velocity of this, and little bit more, the velocity will be more than the velocity of this. At some point, let us say we have given the velocity u is equals to u infinity. U infinity is the inlet velocity. That velocity will be constant. Further moving upward, the velocity will be u infinity only here. That is, the velocity will be u infinity. I can draw one line like this. This line is nothing but the velocity boundary layer. That means only in this the velocity is changing. Wherever you take, only in this point the velocity will be varying. Apart from this, when you move upward, the velocity remains constant here. That means u is equals to 0.99 times of u infinity. That means it almost approaches the inlet velocity. Right? Almost approaches the inlet velocity here. That is what, if that boundary layer is called as the velocity boundary layer here. Right? Why does this happen? That means the region of flow where the effect of shear force due to velocity is observed is called as a boundary layer or velocity boundary layer here. Right? Now what we have done, we have taken the imaginary boundary surface which divides the pipe as boundary layer region. That means this region where the viscous effect and velocity changes are significant, and in this the viscous effect and velocity change are significant here. And one more region is the irrotational flow region, that is this region, irrotational flow region, where the frictional effect are negligible and velocity remains constant here. When we see at this point, the velocity is u average is constant here, right? That is u is u infinity or u average here. The same velocity is there from this point to this point in the pipe here. That is almost all the cross section, all the points in that cross sectional area, the velocity remains constant here. That is u average. When we come to the next point here at this section here, what happens? At some region the velocity is varying here. That means only from here to here the velocity is varying, or from here to here the velocity is varying. When we move further, the velocity remains constant. From this point to this point, the velocity remains constant here. This is the cross sectional pipe cross section what we have taken here. This is the pipe cross section what we have taken, right? That means from here to here the velocity remains constant here. Now further moving that one, this velocity profile will start developing here. The velocity profile will start developing at one certain distance from the main point, entry point, to at some distance the velocity profile will be fully developed. Right? This distance is called, that is from entrance region to the fully developed velocity profile, that region is called as the hydrodynamic entrance region here. That region is called as the hydrodynamic entrance region, right? That means the thickness of this boundary layer increases in the flow direction until the boundary layer reaches the center of pipe and velocity becomes fully developed, right? The region from the inlet of the pipe to the point where the velocity profile is fully developed, that distance is called as the hydrodynamic entrance region here, right? The flow in this region is called hydrodynamically developed flow. This flow is called hydrodynamically developed flow here, because the region because in this region the velocity profile is developed. After this region, where the velocity profile is fully developed and remains constant, from here the velocity profile is fully developed and it remains constant here. This region after this hydrodynamic entrance region is called as the hydrodynamically fully developed region. This flow is said to be fully developed when the temperature of the flow remains constant, right? When the temperature of the flow remains constant, we call this one as the fully developed region here, or hydrodynamically fully developed region. The wall shear stress is highest at the pipe inlet where the thickness of the boundary layer is small. Here you can see the shear stress is more at the pipe inlet, but the this one velocity profile is very less here. But here when we come here, when I write the velocity profile from here, the shear profile from here to this point, what happens? The shear profile will continuously reduce here. This is the tau shear and this is the distance, that is y here, right? This is x here. This is the distance x, this is x here, this is the distance x. This is how the shear profile will be there here. That means at this point is the entrance region. And this side is fully developed region here. Right. This side is fully developed region, this side is the entrance region. This is how the shear stress will be acting here. This is what the entrance region and fully developed region for laminar flow, right? Thank you.